figuring I could use this to like recap how position and velocity graphs relate to each other so that we can see both side by side, right? And the three main types of motion are constant velocity, negative acceleration, and positive acceleration. So this would be good to add to your notes because I'm going to review all the things you need for velocity graphs, but in just one place, right? So what I'm thinking, let's say I have an object that starts in motion. Nice constant velocity. It travels 3 meters forward for every 1 second. We know what the dot diagram for that is going to look like. Nice, evenly spaced dots. And for every second, it goes 3 meters per second forward for 1, 2, 3, 4, 5 seconds at constant velocity. So what would a position versus time graph look like for this? It wouldn't be a horizontal line, but it is going to be a line.
It would be starting at wherever its starting point is the origin, and it would be a linear line going up.
Linear line going up and to the right. So every second, it goes 3 meters forward for 5 seconds, right? So when I do a position versus time graph, I'm going to put an X on the y-axis for position because it's moving to the right. And it travels the same distance upward every second. So I'm going to put a nice linear straight line. And whenever a position versus time graph is linear, now what does the velocity versus time graph look like? A horizontal line. And if you have trouble picturing this in the back of your head, you can think of a T-chart for this. For all 5 seconds of this motion, the velocity was 3. So when I go graph velocity versus time, it'll just be a nice horizontal line with a positive velocity of 3. So my velocity graph, I put V on the y-axis for velocity. It stays 3 the whole time. So a linear position graph goes with a horizontal velocity graph. I'm not going to draw out the no motion or the backward motion. No motion would give you a horizontal graph at the origin. Backward motion would give you a horizontal graph below the origin. So now let's say there is a net force, and that your net force is going to cause your object to go from rest and travel farther and farther and farther every second. In this picture, this is showing acceleration to the right. And so I should have some sort of positive acceleration position graph. Hey, what does positive acceleration in a position graph look like? Some sort of smiley face, like an upward facing curve. And since this is traveling to the right, I'm going to make it look like this. Upward facing curve. A parabolic or quadratic graph, whatever you want to call this curve, whatever you want to call it, but not exponential. That parabolic or squared or quadratic graph, that means that it's traveling faster and faster and faster each second. So my velocity versus time graph is going to start at rest. Think like this is a velocity of about 0. The slope is about 0 here. Then it gets faster and faster and faster. A quadratic graph is going to turn into a linear graph. The positive slope of that linear graph is positive because the acceleration is positive. A velocity versus time graph has slope equal to acceleration. The slope is positive because the acceleration is positive. And if I wanted to put real numbers in there, I could actually take that slope and use it to calculate the acceleration. Last one. If we have positive acceleration, what about negative acceleration? This would be an object that starts fast and goes slower and slower and slower. With negative acceleration, my position versus time graph is going to be some sort of downward facing curve. Right? So I need an object with a downward facing curve. And how do I know it's this downward facing curve and not the other one? I know it's this one because check out the slope here. This slope, which signifies velocity, is fast. A big slope means it's fast. And it ends with no slope. In fact, if I continue in a straight line, that's an object that's not moving. Fast is going to have a high slope. Slow has zero slope. So this is an object that started fast and got slower with negative acceleration. What that would look like on a velocity versus time graph then is a positive velocity because you started fast that gets slower and slower and slower. That acceleration being negative means this slope is negative. So things we should be able to do. We should be able to pair the dot diagram of motion to the position and velocity graphs. In terms of calculations, I'm going to say there's probably 2 calculations you need to know. So let's show you those right now. Just to recap, right? Let's say for a velocity graph, I want to be able to use it to get both acceleration and displacement. So what calculations are you going to need to be able to do? Let's say do examples of both, right? So let's say I have an object that travels at 3 meters per second backward for 5 seconds. I'm not super inventive in numbers here. That's like easy to work with. Then my object is going to slow to a stop over the next 2 seconds. So from 5 to 7 seconds. Once it's stopped, we're going to let it rest. Things I should be able to do with a velocity versus time graph are be able to recognize that this negative means it's moving backward. I should be able to calculate the slope, which is the acceleration of each section. Right? So let's do that one. Where it's a flat line, this slope is 0. So the acceleration is 0. So maybe I'll label it up here where it's out of the way. This slope is equal to the acceleration, but that's 0. It's 0 because it's an object at rest from 7 to whatever seconds. On this nice straight positive slope right here, slope is equal to acceleration. So if you were stuck on the homework problem where you had, you know, the one that has like 6 graphs and it said like rank the accelerations, for that part, you were supposed to like go calculate the slope of each one. So just to review what that looks like, this would be an object whose final velocity is 0. The initial velocity was -3, and it took 2 seconds. Notice that this slope is a positive acceleration, even though the velocity is backward. Right? That slope is a positive acceleration, even though the velocity is backward. That's why it's slowing down. If you were stuck on the lab, you know the lab where it asks like which ones are slowing down and which ones are speeding up? This one is slowing down because the velocity is negative. Right? The velocity is -3. The acceleration is positive 1.5. And whenever these two are in the opposite direction, that means your object is slowing down. You can kind of think the slowing down thing is that this is going from moving at 3 meters per second speed to not moving. Even though the acceleration is positive, it's slowing down because the acceleration is working against the velocity. When they go in opposite directions, think the force is acting against the motion, so it's slowing everything down. Last thing from that graph then, we can use slope to get acceleration. You can use area under the curve to get the displacement, right? Anything associated with distance, position, length, if it is measured in meters, use area under the curve. So if I want to figure out how far this object traveled, I'm going to shade from my function up to the x-axis. That's going to make me two nice enclosed shapes here, a triangle plus a rectangle. Right? And anytime I want displacement, I'm going to calculate the area under the curve. So for this rectangle, its displacement, how long did this object travel backward for, or how far? I can just do a rectangle equation, base times height. This traveled backward for 5 seconds at -3 meters per second, so it went 15 meters back. Even the little triangle is backward. It's backward because it's below the origin. So if I want the displacement of the triangle part, that's a 1/2 base height, where my triangle has a base of only 2, not 7. 2, because it's this little triangle right here, a height of -3. So that still is going backwards. It goes 3 more meters backward. So in total, this object goes 18 meters back. So things I should be able to do with a graph so far. I should be able to connect our dot diagrams to position graphs to velocity graphs. I should be able to do acceleration is the slope of any part of this graph, right? So 0, 1.50. And then displacement is area under the curve. In this case, with a rectangle and triangle, they're both below the x-axis, meaning you're going backward. Any section above the x-axis means you're going forward. So all we're going to do today is add on like this special case. What if instead of having arbitrary forces with like arbitrary motion, what if you had a predictable force, like gravity or something?